if you don't know what a Riemannian manifold is, if you don't know what a determinant line bundle is, there's no way you can ask intelligent questions about alien visitation.
All right, what is up, you guys? Welcome back to another differential geometry stream, and I'm going to start it off with a little bit of an intro before I get into the reading, and we're going to kick that off with a couple of definitions. So, from Wikipedia, we have a Riemannian manifold. In differential geometry, a Riemannian manifold, or Riemannian space, which is specified by M and G, so called after the German mathematician Bernhard Riemann, is a real smooth manifold M equipped with a positive definite inner product G sub P on the tangent space T sub P M at each point P. So a Riemannian manifold can be disambiguated or specified by two parts. The first is the real smooth manifold M, and the second part is that positive definite inner product on your tangent space. Now, it says differential geometry, but that isn't actually spelled out in the book that I'm reading from. However, to put it into context with what I have been reading so far, the chapter I'm in is called The Theory of Curves. And the next chapter, which is coming up real quick, starts to introduce concepts of surfaces, and eventually we get to things like manifolds, but we don't really get to this level of mathematical structure. However, you can realize that a lot of these things are very related, and a lot of the mathematical work that we do on these mathematical objects, it's all really similar. It all involves a lot of things like tangents, tangent space, tangent planes covered with tangent lines. How do we keep track of, organize, compare all of these kinds of different things if you're given a bunch of different curves, a bunch of different lines, a bunch of different surfaces, whatever? Math is a system of organizing and comparing and measuring, etc., with all of these different objects. So that's what a Riemannian manifold is. The second thing I'm going to define is not rigorously a determinant line bundle, but just kind of a line bundle and a fiber bundle, because these are, as we will see here very briefly, topological concepts, but it's very related to another concept in geometry proper, you could say by definition, which is called a pencil, which is actually going to be brought up in what I'm going to read from in the differential geometry book today. So, in mathematics, a line bundle expresses the concept of a line that varies from point to point of a space. For example, a curve in the plane having a tangent line at each point determines a varying line. The tangent bundle is a good way of organizing these. And like I said, this is kind of a specific instance of what's called a fiber bundle, and I'm not going to read the definition for that exactly, because I think the description, the caption for the picture here of a line bundle is more intuitive and it's more informative for the purposes of this differential geometry stream. So we have this picture of a hairbrush, a cylindrical hairbrush showing the intuition behind the term fiber bundle. This hairbrush is like a fiber bundle in which the base space is a cylinder and the fibers, the bristles, are line segments. So when you think of a fiber bundle or a line bundle, you imagine your curve itself is the handle of the hairbrush, and all of the tangents are the collections of bristles that we are then referring to with the concept fiber bundle, line bundle. Now, these are, as it says in, I'm sure you can read the Wikipedia pages on your own, these are formally recognized within topology. However, we're doing things that are very similar in geometry. So what is a pencil? It says, in geometry, a pencil is a family of geometric objects with a common property. Kind of nebulous, but for example, the set of lines that pass through a given point in a plane, or the set of circles that pass through two given points in a plane. Keeps on going, and it says, although the definition of a pencil is rather vague, okay, yes, we agree. But at the top of the page is what I would like to point out here. It says bundle geometry redirects here. So a pencil is a geometric bundle. And it says that this pencil in geometry, a geometric bundle, is not to be confused with a bundle in mathematics, a mathematical bundle. And when you click through the mathematics bundle links here, you sure enough end up at the fiber bundle, line bundle, and yes, Eric Weinstein, we can scroll down and we can read the definition of a determinant line bundle very well, thank you. But I just wanted to start this off because, yeah, I'm going to refer to a geometric pencil very briefly in the reading if I ever get to it. But, all of these concepts are very related, and I just wanted to point that out.
I, however, have been trying to present this material without excess mathematical detail.
The next thing that I want to get to is reading some comments from the audience on my last video, which I just want to say, I should have said this at the very beginning of this, but I just want to thank all of my subscribers from the last two videos because I doubled the amount of subscribers I have on my channel from the last two videos, and I've had an overwhelming positive response from all my videos. So thank you, everyone, and thank you for coming back. I hope that you enjoyed today's differential geometry reading stream, but I wanted to read a comment that this person is probably speaking for a lot of the people who've watched the previous videos, and this is from the Allison1456, and they had watched past the intro, I guess, and they said, "That intro was awesome, but I can't start at the 4th episode. I went back to the first one, but it starts in the middle of a book already. I guess these are not for a general audience." Well, first of all, thank you for commenting that because, like I said, there's probably a lot of people who watched the last few videos or whatever, and they feel the exact same way. The streams, when I watch them even afterwards, they are a little bit chaotic and disorganized, and there's clearly a lot of improvisation going on. But I'm listening to your comments. I take this feedback to heart, and I do want these differential geometry streams to be more understandable and accessible, and I don't want them to be so recondite and obscure. I want there to be things where even if you don't learn about the differential geometry specifically, hopefully there'll be something about math in general that you take away, or you're entertained by my antics. I don't know. So thank you, the Allison1456, for your comment. Also, I will say, though, as I'm nearing the end of this second chapter, or the first substantial chapter in the differential geometry book, I am going to do in 2 or 3 streams from now a chapter review, recap, maybe speed run if you want to call it that, of these first 24 sections that are the theory of curves, before going into then the first fundamental form and the fundamentals of tensor calculus, which is what the next proper chapter involves in the differential geometry book. So that's a really good comment. I also then wanted to apologize to Jean-Gaston Darboux because in the last stream I went on this impassioned rant about, recognizing mathematicians and stuff like that. And then I get to where I'm reading in section 16 and I just totally botched it and forgot this guy's name. So respect for Jean-Gaston Darboux. And now we're going to get to another comment here. This is from Proximity Gaming 8253, and I just want to give this person the first differential geometry stream audience award. I'm just probably going to give these out every single stream to people for giving good comments, if there are comments, but this one is a great comment. I need you guys to keep me on my toes, keep me rigorous, call me out when I'm too loosey-goosey and stuff, or when I'm just, really off on a tangent and I'm just kind of digging through breadcrumbs, and it's just kind of really vague and obscure and stuff. So I really liked this comment. At 34 minutes and 18 seconds, Proximity Gaming says, I'm pretty sure that one intersection just means a repeated real root, but you're right about there being complex roots if there are 0 intersections with the x-axis. 100% correct. Spot on. This was in the last video. I was on a rant about complex analysis. I wanted to, just give the most brief outline of going from motivating complex variables and then go all the way to Cauchy's residue theorem. But obviously I skipped a lot of steps, and I was on a rant about the motivation for complex numbers, which involves quadratics. It also involves cubics, and that's what I'm going to start off on today, is fleshing that out. And I totally gaffed the analysis of the roots of quadratics, which is pretty embarrassing, frankly, especially because I'm doing this whole thing about hardcore differential geometry and can't even get the facts straight on the roots of quadratics. You know what I'm saying? So Proximity Gaming 8253, I appreciate that comment because, it's keeping things sharp, keeping things real. We want to be accurate here and stuff. So that's where I'm going to kick things off more properly from, is fleshing out this comment. So thank you, Proximity Gaming 8253. So you could be a little bit disoriented, like what the heck is Anthony talking about right now? This is what I'm talking about. So we've got quadratics, right? And we're going to draw in our analytic Cartesian coordinate system here. We have 3 possibilities. Possibility number 1 is we have a quadratic that intersects the x-axis twice. You could call each of the intersections the roots A and B, and then it leads to an easy factorization knowing those roots in order to obtain the equation for this parabola. That's the first possibility. Second possibility is you could have a parabola which just intersects the x-axis once. You don't get complex numbers here, but you get, again, a really easy representation of your quadratic, real repeated root, repeated factors, straightforward. The third possibility, which is what Proximity Gaming was referring to, which I totally gaffed, brain fart, brain fog, forever lost, just could not pull out of the ether, embarrassing, which is a quadratic which does not touch the x-axis at all. And you could say from algebraic reasoning, well, quadratics are polynomials, lines are polynomials, and a line is a first degree polynomial. All lines that are not, horizontal are going to be guaranteed to cross the x-axis at least once, one crossing, one root. It's the same as the first order of a line polynomial, x to the power of 1. So you would expect that you could just easily generalize that accordance between the order of the polynomial and the number of roots that it has to quadratics. And you could say, well, we expect that these second order polynomials will have at most 2 roots according to the order of that polynomial. And well, you look at the 3 examples that I just laid out here, and that third example is a little tricky if you're someone living in the early Renaissance, because you could say, Descartes, he came up with this analytic geometry stuff, Cartesian coordinate system, but there are no crossings of the x-axis with this third case here. And you could also kind of do maybe some like weird loosey-goosey transform your coordinate system and make it so that these quadratics that don't ostensibly cross the x-axis at all, you could maybe do some hand-waving stuff and say, oh, you know what? All right, we've got the quadratic formula here, minus 4ac all over 2a. So sure, quadratic formula, we could attribute to the quadratic that does not cross the x-axis at all, we could attribute what are called roots to this quadratic, but some early Renaissance guys might look at this and say, well, you could transform the coordinate system, and even though your calculations involved taking square roots of negative numbers, we're not really sure what that stuff is all about. However, the story becomes a little more tricky when you get to the next higher polynomials, cubics, because every single cubic is guaranteed. It's kind of like how a line is guaranteed to cross the x-axis once. A cubic is also guaranteed to cross the x-axis at least once. You could have a cubic that crosses 3 times, of course, and you have 3 real roots, and it's the same reasoning: x minus a, x minus b, x minus c, easy factorization of the case where the cubic blatantly crosses the x-axis 3 times. But, if you have a cubic that it's guaranteed at least to cross the x-axis once, and then you had that reasoning about the order of the polynomial being in accordance with the number of algebraic roots of this polynomial, you look at the cubic that crosses the x-axis once and you say, well, where are the other 2 roots? And so we now know from being in the future, we're just going to skip over all this, what the actual answer really is. If you have ax cubed, where a is a scalar coefficient, plus bx squared plus cx plus d equals 0. For the ease of writing, we're going to introduce delta naught and delta 1, where delta naught is equal to b squared minus 3ac, very reminiscent of the determinant for a quadratic, I will add. Then you have delta 1 equals 2b cubed minus 9abc plus 27ad squared. Then you let, again, for the sake of writing, we're going to introduce c and, is that an omicron or an epsilon? I'm not sure. It's another Greek character. I'm sorry. But we have c, which is equal to the cube root of delta 1 plus or minus the square root of delta 1 squared minus 4 delta naught cubed, all over 2. And we write that this omicron, I believe then, is equal to negative 1 plus or minus the square root of negative 3 all over 2. I will point out here before continuing on that this omicron variable is a constant, negative 1 plus or minus square root of negative 3 all over 2. Each of these omicrons are complex conjugates of each other, which is that the real component is the same, but you have the negative complex or imaginary component of each other. So the first omicron would be negative 1 plus the square root of negative 3 all over 2. The other one is negative 1 minus the square root of negative 3 all over 2. So they have the same real component, negative 1/2. And, okay. Thus, the 3 cubic roots are x sub k, where k is equal to 0, 1, or 2, equal to negative 1 over 3a times the quantity b plus omicron to the k times c plus delta sub 0 all over a denominator of omicron to the k times c. So this is our modern analytical look up the answer. This is how you get any cube root, because ax cubed plus bx squared plus cx plus d equals 0. That's the most general cubic you can possibly have. You're always going to get the answer, just like the nice quadratic formula. So we like things like that here in 2024, right? But things were not always like that, okay? Of course. Where did this come from? And so we return now to so in the early Renaissance, kind of like how I alluded to, they didn't have the formula that I just flashed on the screen. They didn't have the general cubic roots for ax cubed plus bx squared plus cx plus d equals 0. So it started off with this guy, Scipione del Ferro. And this guy lived in the early Renaissance. He was born in 1465, died in 1526, to give you a little time perspective. And he had a solution for cubic roots if the cubic was of the form x cubed plus mx equals n. But he kept this a secret until he was about to die. And he's on his deathbed, and he gives the solution to his student, Antonio Fior. Okay, these guys are all Italian. Go figure, with the whole, what I mentioned about, nation states not existing. And so mathematical progress was a little bit siloed off into whatever different languages people were speaking. So this is what the Italians were working on in the early Renaissance, right? So anyways, this guy Fior, he gets a hold of his teacher Del Ferro's method for this subset of cubics. And he challenges this other guy, Niccolo Tartaglia, which, again, for time perspective, this guy was born in 1500 and he died in 1557. So he's more or less not exactly a contemporary of Del Ferro, but he's a little bit after. So this guy, Fior, who was Del Ferro's student, challenges Tartaglia. He says to Tartaglia, hey, let's each of us put up some money, and we're going to have a competition to see who can solve more roots of cubic equations. Whoever wins will get the entire purse. And so Tartaglia is like, all right. But the thing is Fior, who was the student of Del Ferro, he had cubic problems of the form x cubed plus mx squared equals n, whereas Tartaglia had the same x cubed plus mx equals n cubics that Del Ferro had worked out his solution for, and Tartaglia similarly had a solution for those same kinds of cubics. So when it came down to the competition with Fior, Fior was not able to solve as many problems as Tartaglia because those x cubed plus mx squared had that quadratic term in there. He was tripped up by that, and so Tartaglia won. Now, there's this guy, Girolamo Cardano, who was born 1501, died in 1576. So he's a contemporary of Tartaglia. He hears about this and he's like, hey, that's really interesting. He's working on this book called Ars Magna, which would then become a classic algebra text in the early Renaissance. And so, he's collecting up all of his algebraic insights into this book that he's working on. He hears about what Tartaglia and Fior were doing. And so he goes to Tartaglia and he's like, hey, man, I heard about this cubic contest that you had. What was your method for solving the roots of the cubics of the form x cubed plus mx equals n? And, Tartaglia tells him, and Cardano is working on his book, and he says, okay, I tell you what. He says, oh, that's a great method, Tartaglia, really cool. I am not going to publish that in my book, Ars Magna. I'll give you time to publish it on your own, and then, I'll publish Ars Magna. Everyone will have, made a publication about cubic equations, and we're all going to be baller scientists or baller mathematicians that are going to be remembered by history forever, and it's going to be great. But so that was a respectful move from Girolamo Cardano, I would say. However, Tartaglia then took his sweet time, years, like 7 years. And Cardano was like, okay, what the heck, man? I'm going to publish stuff in Ars Magna eventually at this point because you haven't done anything. And for whatever reason, Tartaglia started getting pissed, and he starts challenging Cardano to another math-off cubic root-finding competition. But Cardano's like, I don't want to do this. And instead, his Cardano's student, Ludovico Ferrari, shows up and takes up Tartaglia on this challenge. And I don't think Ludovico Ferrari is related to like the modern car family Ferrari, because let's be real, early Renaissance, if you've got the time and the resources to be doing all this stuff, either you're a really rich, well-off guy or you're a monk. There's no in between. And this Ludovico Ferrari guy is a monk. And so his branch of the Ferrari family ends with him. But Ferrari goes and challenges or takes up Tartaglia on this challenge and actually wins. And Tartaglia then gets disgraced and loses all of his money. And sad to hear that. But Girolamo Cardano then continues to publish findings and results involving Tartaglia's method. And specifically, Cardano noted in the finally published Ars Magna that Tartaglia's method sometimes required methods or calculations with square roots of negative numbers, and he showed calculations of how to extract these square roots of negative numbers. And this is actually the first instance of using imaginary numbers. And so that's why we consider perhaps Cardano in Ars Magna to have discovered complex numbers at all. He didn't flesh out or give, like a physical intuition explanation or anything like that, but it started there. And then to connect this, to bring it full swing with what I was talking about in the complex analysis subroutine speedrun of the last stream, was that Augustin Cauchy, he single-handedly basically then developed the branch of mathematics we know today as complex variables from basically what Cardano had left off on. Yeah, there was, Euler and e to the x is super critical to complex variables. So I do basically just ignore all of that. However, I think it's, the reason why I give Cauchy a lot of credit, not just because complex values and residue theorem is really cool. It's a powerful tool in mathematics. You have to do all this rigorous work in order to climb up, and you see the 10,000 foot view of mathematics once you get there. Another point is that the contemporary of Cauchy, Jean-Augustin Fresnel was a physicist. And at the time, the state-of-the-art understanding of light was based on Newton's understanding of light, which attributed light as a particle. It was like the corpuscular understanding of light. That was like the best at the time of Cauchy and this other guy, Fresnel. But Fresnel, as a physicist, was working with properties of light such as birefringence, refraction, diffraction, etc., which were insufficiently described by a particle model for light. And long story short is that Fresnel's innovations in physics combined with Cauchy's innovations in math, science overall was at a critical mass for understanding light that we could then, from Maxwell, have a wave theory of light that's described by Maxwell's equations, and then, you keep on going on and on from there. This is all to say, very roughly, that had it not been for Fresnel to take care of the physics innovations, investigating properties of light that are insufficiently described or explained by a particle theory of light, Fresnel worked on the physics. Cauchy was working on math. Of course, there's others that deserve credit, Euler and everyone, but Cauchy single-handedly developed complex variables. How are you going to describe alternating currents and stuff without complex variables? You're going to have a bad time. They built all that up, and then Maxwell comes along. He's independently looking at things involving electricity, but then by the time that he realizes, oh man, the speed of light is the same as the speed of an electromagnetic wave. They're the same. We get closer to having a wave, a comprehensive wave theory of light, or a modern wave theory of light. So there's a lot going on there, and I just wanted to, continue to add in some of the history of science, physics stuff, because I don't know, maybe there's somebody out there who likes it. So continuing on with reading from the Differential Geometry book, we are in section 19 of chapter 2, which is the theory of curves. That's the chapter, and the section is contact, the osculating sphere. We've already seen the osculating plane, the osculating circle, and now we are at the osculating sphere. I had a conjecture at the beginning of these streams that would say, oh, I bet this is going to be a generalization of properties that are familiar in the context of an osculating plane and circle, but we're just going to add more by being in higher dimensions when we start working with an osculating sphere. We're going to see how that pans out. So let us consider two curves, C and C star, which have a point, say, P naught in common. This is what we're given. In a neighborhood of P naught, these curves may more or less differ from each other. We will investigate this situation in detail and characterize it in a precise manner by introducing the concept of contact. Specifically, the next page or two is going to just take that paragraph and restate it in specific, rigorous mathematical form. First of all, there are two possible cases when we have these curves C and C star that are making contact at a point P naught. Either the tangents to C and C star at P naught are different from each other, or B, they coincide. Let C be allowably represented by the vector x of t, which is equal to f1 of t, f2 of t, and f3 of t along each of its respective dimensions, and C star by the vector x of t star, which is equal to the functions g1 of t star, g2 of t star, and g3 of t star along each of its respective dimensions. And let P naught correspond to the values t equal to t naught and t star equal to t star naught. I will remind you guys that allowably represented here just means that we do not have all of the derivatives of these vector parametric representations vanishing. So when you do derivatives of these individual functions, f1, f2, f3, you can't do a first derivative, say, and then all of them go to 0. That is not an allowable representation. So just to give you a recap, so you don't have to go back 3 or 4 videos and then be disoriented in the middle of a math book. Then in both cases, A and B, we have that x of t naught is equal to x of t naught star. So like I said, just giving more mathematical rigor to the paragraph that was on the previous page. Moreover, in case B, and only in this case, the two vectors ddt of the vector x evaluated at t equal to t naught and ddt star of x evaluated at t star equal to t star naught are parallel, since these vectors are tangent to C and C star at the point P naught. We introduce now the arc lengths of C and C star as parameters in such a manner that both curves at P naught have the same orientation. Let C be represented by the vector x, which is parametric in terms of arc length, where the functions of each of the dimensions of x are alpha sub 1 of s, alpha sub 2 of s, and alpha sub 3 of s. Similarly, for the curve C star and its vector parametric representation in terms of its arc length, which we will refer to as s star, the functions of the particular dimensions of this parametric vector are beta 1 of s star, beta 2 of s star, and beta 3 of s star. Let these be the representations thus obtained. They are of class R if the above representations are of this class, which you can see in the arc length section. And when I say class R, that means that they are R times differentiable. We denote by S sub 0 and S star sub 0 the values of the parameters corresponding to P naught. So they're the arc lengths S naught and S star naught that then in the vector parametric representations in terms of arc length, we are then at the point of contact between the curves C and C star. Using these aforementioned vector parametric representations in terms of arc length of these curves, in the case that the tangents of the curves coincide at this point of contact, we now have simply that alpha sub I of S naught is equal to beta sub I at S star naught, and DDS of alpha sub I evaluated at S equals S naught is equal to DDS star of beta sub I evaluated at S star equals S star naught for I equals 1, 2, and 3. While we can visually distinguish only between the two cases A and B, we are able to characterize the case B in more detail by analytical methods, that is, by taking into account the higher derivatives of the vector parametric representations x of S and x of S star. For this purpose, we make the following. Definition 19.1. This is the definition of contact. A curve C has contact of order M exactly with a curve C star at a point P naught if, when using the vector parametric representations of the curves C and C star in terms of their arc lengths respectively, if at P naught we have alpha sub I of S equals beta sub I of S star and DDS mu of alpha I, that is to say the muth derivative in terms of arc length of the function alpha sub I is equal to correspondingly DDS star mu, so the muth derivative in terms of S star of beta sub I, where mu is equal to integers up to and including m, so mu is equal to 1, 2, etc. through m, and I is equal to 1, 2, and 3. So these relations hold for each entry or each dimension of the vector parametric representations of the curves that are in contact here. And if also the derivatives of order m plus 1 at P exist, then we have that the m plus 1th derivative in terms of S of alpha sub I is not equal to the m plus 1th derivative in terms of S star of beta sub I for I equals 1, 2, and 3. I'm going to take a moment to pause here because this is going to be referred to in the proofs that are about to happen in the next couple of pages. This definition of contact has two parts. You can look at the first part as specifying things about the derivatives up to the mth derivative. So these are going to be equal. However, if this is not saying that this is guaranteed by the definition of contact, if the derivatives of order m plus 1, this is the second part of the definition, if you have that next derivative beyond the mth derivative, so you have the m plus 1th derivative, then these derivatives are not equal at the point of contact P naught. So this definition right here of contact and the two parts, an easier, relatively easy way to kind of compartmentalize this when we're moving forward is, okay, curve C star. We have at least m derivatives of the vector parametric representations of these curves. When we have contact, we're going to get that these, not only does the value of the curves equal to each other at this point, because otherwise there would be no contact, but being that we specify that the tangents are in the same direction, which we can do arbitrarily by picking the sense that we define the transformation going into arc length, right? Then the derivatives going from 1 to m at this point of contact, when you're evaluating at the point of contact, they're going to be equal. But then the second part of this definition is saying, okay, that everything was up to the mth derivative. If you have an m plus 1th derivative, they're not going to be equal. For curve C star, where we're looking at the entries of the vector parametric representation of C, that's alpha. The entries of the vector parametric curve C star, that's beta. When you have the m plus 1th order derivative, alpha derivative, beta derivative, not equal at the point P naught. Because we're going to come back to this definition throughout me reading this section. Of course, this definition has a meaning only for those values of m which are at most equal to the class of the functions x of s and x of s star. Hit a little bit of the coffee real quick. Strain it with chopsticks, the only way to properly optimize the vortex of stirring your coffee at the molecular level. Try not to drip coffee from my mustache on my shirt and my suit jacket. Here we go. According to this definition, in the above case, A, C has contact of order 0 with C. That is to say, when the tangents to C and C star at P naught are different from each other. There's contact of the order 0, which is an important thing to point out because when you look at the first part of the definition of contact, mu is allowed to be 1 through m, but it is not specified or allowed to be 0. However, it's an important caveat that we can still have contact of the 0th order, which is the case when the curves evaluated just straight up equal each other at that point, but the tangents are not in the same direction. So you've already broken the definition at your first derivative. That's not to say there's no contact. There is still contact, right? Because you could geometrically look with your eyes and you'd be like, oh my gosh, they're still touching, but you don't have contact because the derivatives don't work out. Okay, well, you do have contact. It's just of the 0th order when your tangents don't have the same direction. So contact of first order is also known as ordinary contact. Contact of second order is known as stationary contact or osculation. And contact of third order as stationary osculation or superosculation. Definition 19.1 may be geometrically interpreted as follows. We consider the development of x of s in powers of the quantity s minus s naught, where s is a variable and s naught is a particular arc length that these vector parametric representations are being evaluated at, namely the point of contact itself, P naught, which is a point on the curve C and C star. But this S naught is an arc length that we're then traversing along the functions representing the curves that we then specify the point of contact at. But S is just the variable arc length. So we consider the development of x of s in powers of this quantity s minus s naught according to Taylor's formula. And now is a good time to revisit Taylor's formula because at the end of the last section, section 18, there was a problem which, if you were listening to the stream at the very, very end, I was definitely starting to fall apart, but the actual solution to the problem, there was all this algebra, and I skipped over reading it. And so maybe you were trying to follow along on screen and you're just like, what the heck happened in this problem? The last problem of section 18, the method of the solution, I like to call Taylor series and cancel, because that's all it was, is you just took your formula, your function, and you expanded it out by Taylor series. You did another function, you expand it out with the Taylor series, and then you look at the two expansions, you cancel them out, and then at the end you get oh, h equals 2r times sine of s over r equals s minus s cubed over 3 factorial times 2r squared. Literally all you had to do to get that is Taylor series and cancel. But at this point, for posterity's sake, for good measure, we need to go over Taylor's series, Taylor formula, Taylor's theorem. That's 3 different Taylors, or are they? Taylor series, Taylor formula, Taylor theorem. What's the difference? Okay, there's really no difference. There is, but it's very subtle. So you can make a flashcard, and you could say Taylor series, an expansion of this function about a particular point A, and then you could rattle off what's on the back of the flashcard. You have the sum from n equals 0 of the nth derivative of the function evaluated at A over the n factorial times x minus A to the nth power. And then you could iterate out all of the terms of this series. And then you could say you're done. You've just defined the Taylor series because, hey, here's your flashcard. That's all you need to know, right? Well, Taylor's series or Taylor's formula could be interpreted that way. However, there are caveats to this definition, and that's where Taylor's theorem comes in. So this is returning to a book I've mentioned in previous streams, Introduction to Analysis. There are better ones out there, of course, like Baby Rudin. That's considered a more rigorous intro to analysis book, if you will, or like analysis at the undergraduate level than this, which I would agree with. I read this one right here, Intro to Analysis, alongside reading Baby Rudin, which I forgot if it's called Fundamentals or Foundations of Mathematical Analysis, because I just keep on calling it Baby Rudin. But Baby Rudin is more rigorous because it starts off immediately considering, the necessity of square roots, square root of 2, and all that kind of stuff. This is a little bit more of like lecture notes outline, this Intro to Analysis book. But it's like, these concepts and stuff don't just live in books. They live in the minds of the scientists and mathematicians and physicists and the people who use them. And who's to say what goes in the book in the first place, right? Like this guy, Erwin Kreyszig, obviously had a little bit of a historical leaning by all of the various mathematicians that are involved in the development of the theory of curves that he threw into this book, So, who's to say, right? But going back to this Intro to Analysis book, here's a version of the definition of Taylor's theorem, right? Let U be an open interval in R and let the function f mapping from U to R the real numbers, of course, be n plus 1 times differentiable. Then for any A and B in U, we have f of b equals f of a plus f prime of a over 1 factorial times the quantity b minus a plus f double prime of a over 2 factorial times the quantity b minus a squared plus etc. Which that's exactly what's on the back of this note card, Taylor series, okay? But the key difference between saying, oh, Taylor series, Taylor formula, plug and chug, Taylor series and cancel, it's the statement of the theorem, the logic involved. It's if you have this function, if it's n plus 1 times differentiable, if A and B are in the domain that f maps to R, then that implies that you have the Taylor series expansion of that function about those points, right? So it's very subtle because you could just write down a formula sheet and have Taylor series, Taylor formula written on them. But then when you go to actually do stuff with it, those little details of the statement of Taylor's theorem can get lost, and then you're going to have a bad time. And Taylor series and cancel is very convenient. So we want to make sure that you can still be able to use that when you start running around in math land. Anyways, back to differential geometry. The curve obtained by taking the sum of the first terms of the above development up to the term containing the power, quantity s minus s naught to the kth power, inclusively, is called the kth approximating curve of C at the point P naught. In this terminology, the tangent at P naught is the first approximating curve, etc. Then, contact of order m is equivalent to the coincidence of the first, second, etc. through mth approximating curves of the curves under consideration at the point of contact. Now, we're going to have a rough definition of a surface here. This is going to be a little more rigorously defined in the beginning of the next chapter, where curves, tensor calculus, first fundamental form are starting to be introduced. But we introduce a rough definition of surfaces here, which is as follows. In order to continue our present investigation, it is necessary to consider also surfaces, but actually only very special, simple types. Postponing a detailed investigation to section 24, that's the beginning of the next chapter, it is, at this stage, sufficient to say that surfaces are point sets in Euclidean space which, at least in a sufficiently small neighborhood of any of their points, can be represented in the form function g of x1, x2, x3 is equal to 0, where g is a function of class m, which is greater than or equal to 1, whose partial derivatives of the first order do not all vanish at any point. Two quick things here. The definition of an allowable representation is being echoed here a little bit, but it's very subtle. When we say that the partial derivatives of the first order don't vanish at any point, it echoes that a little bit. Yeah, so the other thing, and this is brought up in earlier sections of this chapter, is solving this representation of the function g in terms of one of its distinct variables. So solving for x1 in terms of x2 and x3, or solving x2 in terms of x1 and x3, representing the function g that way. That is going to be done in one of the proofs that is going to come up here in a little bit, so just a heads up. Let us now define the contact of a curve with one of these special simple surfaces. Definition 19.2. A curve C has contact of order M exactly with a surface S at a point P naught if there exists at least one curve C star on S, the surface, which has a contact of order M with C at P naught, and there does not exist a curve on S which has a contact of order greater than M with C at P naught. We will now consider planes and spheres which have a contact with an arbitrary given curve. First, it is clear that a plane which has contact of first order with a curve C at a point P naught must pass through the tangent to C at P naught. At any point of C, there exists a whole pencil of planes of this type in which the corresponding osculating plane of C is also contained. So there you go. We're bringing it back full circle with what was in the beginning, towards the beginning of this differential geometry stream, which is the geometric pencil. It's a concept which is similar. It's a cousin maybe to the topological concept of a line bundle, vector bundle, or the determinant line bundle, as Eric Weinstein likes to throw around casually on podcasts. Anyways, so it's a collection of these tangents at the point that we have contact for. We're referring to the collection of tangents as a pencil. Theorem 19.1, which we are going to prove. At any of its points, a curve has contact of second order at least with its corresponding osculating plane. And here's the proof. Let the curve capital C proper, given by its vector parametric representation in terms of arc length x of s, be any curve. We develop x of s in a series of powers of the quantity s minus s naught by Taylor's formula, where s naught may correspond to any point p naught of the curve C. When we take the terms of this expansion only up to that which contains x double dot of S naught inclusively, we obtain a representation of a curve C star. This curve has a contact of second order with C at P naught. Since the osculating plane of C at P naught is spanned by the vectors x dot at S naught and x double dot at S naught, the curve C star lies in this plane. By the definition of contact, C therefore has contact of at least second order with that osculating plane at P naught. If the torsion is non-zero at P naught, which you can go back 2 streams and find out all about torsion, the contact is exactly of second order, as can be seen, for example, from the canonical representation of that curve. As a preparation for the investigation of spheres which have contact with a curve, we state the following. This is Lemma 19.2, which will be proved. Let C be a curve which can be represented by an allowable representation x of S, which is equal to function alpha sub I of S of class r greater than or equal to m, with arc length S as a parameter, and I is equal to the number of dimensions that this parametric representation is given in terms of, probably 3 for the sake of this. Furthermore, let the curve capital C proper have a point P naught, which is at the arc length specifically S naught, in common with the surface S, which in a neighborhood of point P naught has a representation given by the function g of x1, x2, x3, which is equal to 0, which that function, giving the representation of that surface, is of class r greater than or equal to m. That is to say, it is at least m times differentiable, where its partial derivatives are m times differentiable. Then C has contact of order m exactly with S at P naught, if and only if, so the proof is going to show forwards and backwards, just a warning, the function P of S is equal to the function g evaluated at the function alpha sub 1 of S, the function alpha sub 2 of S, and the function alpha sub 3 of S, and its derivatives with respect to S up to the mth inclusively vanish at the point P naught, while the m plus 1th derivative, if it exists, does not vanish at this point. That is, P of S naught equals 0, the muth derivative with respect to arc length S of P evaluated at S equals S naught is equal to 0, and we have that mu here can be first, second, etc. through mth derivatives. Correspondingly, the m plus 1th derivative in terms of S of P evaluated at S naught is non-zero. So derivatives up to m, 0, m plus 1th, not 0. And just before I dive into the proof, we can see that this lemma 19.2 echoes the definition of contact for 2 curves, where you have the value of the curves equal each other. Otherwise, it's just not fitting with our intuitive notion of contact at all. And up to the order of contact, so we have mth order, then we have all of these derivatives equal 0. But then if you also have an m plus 1th derivative, it's not 0. But lemma 19.2 isn't between 2 curves, it's between a curve and this simple rough definition of a surface. It could be just like a subset of like a general surface, but you have these specifications about the partial derivatives not vanishing in a local neighborhood of the surface, and you could just cut away parts of the surface that you don't want to worry about if it doesn't have that differentiability. So Now we're going to go into the proof. And like I said, there's two parts to the proof. There's going to be a forward direction, and then there's going to be the reverse, because in the Lemma 19.2, there's that if and only if, okay? So, proof. If C has contact of order M with S at the point P naught, then according to the definition of contact, there exists a curve C star on the surface S, which has a contact of order M exactly with C at P naught. We denote by S star the arc length of C star. Let then the vector X parametric vector evaluated at this particular arc length variable S star of the curve C star equals these functions beta sub I in terms of S star. Let that be a representation of C star, so that at the point P naught, C and C star have the same orientation. Okay, that's not so bad. The point P naught may correspond to the value S star equal to specifically S star naught. Since C star lies on S, we first have that the function G evaluated at in the first dimension along the function beta 1 of S star, in the second dimension along the second function beta 2 of S star, and in the third dimension by the function beta 3 of S star. This function G entirely evaluates to 0, and by successive differentiation with respect to S star, we obtain these at first horrendous looking sums, but I'm going to explain what these are. The sum from I equals 1 to 3 of partial G partial xi times d beta sub I ds star equals 0. And then we have a sum of sums where the outer sum is on the index I from 1 to 3, and then we have an inner sum which is on the index k equals 1 to 3, and the terms of summation are given by partial squared of g partial xi partial xk times d ds star of beta sub I times d ds star of beta sub k, and that concludes the double sum. But then this is added onto an additional sum, which is from I equals 1 to 3 of partial g partial xi times d squared beta sub I ds star squared. And this is all equal to 0. These look horrendous. I'm not going to lie to you. And they're a little bit atrocious to read as well. However, we're doing, successive differentiation with respect to S star, and we're looking at these, we're looking at the function G, okay? G is a multivariate function here. G is in terms of, there's like a first, second, and third component to G. Within those components, we're using the functions beta 1, beta 2, beta 3. And we're doing successive differentiation. So hopefully you're connecting together that this is a little bit of calculus 1, or I guess maybe it's calculus 3. Not sure, but we're going to do the chain rule here. So we've got another math flashcard. Chain rule. What is it? The derivative of, we have a function of a function. You take the derivative of the outside composed with the inside times the derivative of the inside. But then you look back at this and you're like, oh my God, how am I going to apply that calculus flashcard definition to this? Well, that's when you go to Wikipedia and you look at the chain rule page, which I've got open for you here, and you scroll down to the higher derivatives, and we have, Fa di Bruno's formula generalizes the chain rule to higher derivatives, assuming that y equals f of u and u equals g of x, and the first few derivatives are dy dx equals dy du times du dx. Then we have d squared y dx squared equals d squared y over du squared times the quantity du dx squared plus dy du times d squared u over dx squared, and you can keep on going for higher derivatives. And so if you really wanted to know about it, you could click on the page for Fadi-Bruno's formula, and you can sit down with pen and paper or whatever you want, or maybe you're just a genius and you could do that in your head. In which case, I'm honored that you're watching my differential geometry streams. If you can calculate these higher order derivatives just off the dome and you're watching my videos, awesome. I hope you're subscribed, and I'm glad to have you here. So then, we go back to the differential geometry book and we read 19.4b and we say, oh my gosh, this is really just the chain rule for higher order derivatives, and we only did a second order derivatives, and we have some summations on top of them. This is not bad. This is not bad at all. We can live with this, right? So they're saying, okay, we have all this stuff about C star. We can write the representation of the function G. We can do chain rule derivatives thanks to Fadi-Bruno's formula, and it says, etc. Why do we care? All of these relations are identities in the arc length S star. So we're going to use these identities to compute or calculate the definition of contact that we're trying to we're trying to expand this out to not just be between two curves, but between a curve and a surface, right? So that's what we're doing here. And we're using the chain rule higher order derivatives to compute that. So since C has contact of order M with the curve C star at P naught, then according to the definition of contact, we have that alpha sub 1 at S naught is equal to beta sub 1 at S star naught, and we have that the muth derivative in terms of S of the function alpha sub I evaluated at S equals S naught, and the muth derivative in terms of S star of beta sub I evaluated at S star equals S star naught, for mu equals integers 1 through m, those derivatives are equal. And if the m plus 1th derivative also exists, then according to the definition for contact, which we assumed that the necessary aspects of the definition of contact are fulfilled by the curves C and C star, where C star we constructed by the definition of the surface that we were given. So we're playing within the rules of the definition for contact between two curves properly. According to that, we have that these m plus 1th derivatives, specifically in terms of S for the function AI, or alpha sub I, and in terms of S star for the function beta sub I, these are not equal. The m plus 1th derivatives are not equal. So we're just going from definitions and we're showing that what we were given, we can get the definition out of that. Setting S star equal to S star naught in the humongous partial derivatives and stuff that we have due to the higher order chain rule, Fadi-Bruno's formula. Then, by means of what we just computed as far as the mth derivatives and the m plus 1th derivatives, then we can eliminate from what we just calculated the derivatives of the functions beta sub I of S star naught. And this procedure then yields the conclusion of Lemma 19.2. All right, so now that we had shown by this procedure that we have yielded the conclusion of Lemma 19.2, we will now show the converse, because to reiterate, Lemma 19.2 is an if and only if proof, so you have to do both directions. And this is going to be a contradiction. So the things that are assumed in the beginning of this are going to be then contradicted by the end of this leg of the proof, and that's what it's going to be. By hypothesis, partial g partial x sub I is non-zero at any point for at least one value of I equals 1, 2, and 3. If at the point P naught, say partial g partial x cubed without loss of generality is non-zero, and by that I mean you could choose partial g partial x2 or partial g partial x1, and the logic of the proof will be the exact same. But you just only need to show partial g partial x cubed. It just makes it a little more straightforward to read. Then, at least in a certain neighborhood of P naught, we can represent the surface S in the form x cubed equal to the function h, which is in terms of x1 and x2. Like I said, you take that function g of x1, x2, x3, and then you re-represent that in a different form where you've solved out x1 in terms of x2 and x3, and that's how we're going to move forward. So, in consequence of the conclusion of Lemma 19.2, so again, we're going backwards, so we're assuming that we already have the conclusion of the Lemma 19.2, and that from going backwards from that, we're going to get the conditions or the assumptions that are in the beginning, the forward direction of Lemma 19.2. In consequence of this equation and the equations obtained by differentiating m times are satisfied at the point P naught by the functions alpha sub I s and its derivatives. Setting s star equal to s, then the function beta 1 in terms of s star is equal to alpha 1 in terms of s, and beta sub 2, the function, in terms of s star is equal to the function alpha sub 2 in terms of s. Then beta sub 3 can be written as the function h transformed from the variables x1 and x2 to the variables beta 1 and beta 2. This is so that the terms of contact between the curve and the surface are also satisfied for I equals 3. But this contradicts what was assumed, right? That partial g partial x cubed is non-zero. And we just showed by calculation that they are zero. This completes the proof. This lemma permits us a more detailed geometric characterization of the contact of a curve with a surface. And now we get Theorem 19.3. Let C be a curve of class R greater than or equal to m plus 1, which has contact of order m with a surface S of class R at a point P naught. If m is even, then C pierces S at P naught. If m is odd, then, in a sufficiently small neighborhood U of P naught, C lies on one side of S. And for this, we have a little short proof. Let C be represented by the vector parametric representation x in terms of arc length S, which is equal to the function alpha sub I of S, so that P naught corresponds to S equals 0, and let the function g of x1, x2, x3 equals 0 be a representation of S valid in a neighborhood of the point P naught. Then, by means of Taylor's formula, we have, in consequence of the result of the lemma that we had just proved, that P of S is equal to the function g evaluated at alpha 1 of S, alpha 2 of S, and alpha 3 of S respectively, which is equal to, by this Taylor formula or Taylor series or Taylor theorem expansion, S to the power m plus 1 over the factorial of m plus 1 times the m plus 1th derivative in terms of arc length of the function P evaluated at theta times S, where theta is non-inclusive between 0 and 1. Since the m plus 1th derivative of P naught in terms of S is non-zero as a result of the lemma that we had just proved, then for sufficiently small values of the absolute value of S, also we have that the m plus 1th derivative of P of theta of S in terms of S, the derivative is in terms of S, that is non-zero. And in consequence of the continuity of the m plus 1th derivative, the sign is the same in both cases. Now, we're going to split this and say, let m be even. then s to the m plus 1 is greater than 0 if s is greater than 0, and s to the power of m plus 1 is less than 0 if s is less than 0. Now, the other side of splitting it off, if m is odd, then s to the power of m plus 1 is greater than 0 for all values of s. And that completes the proof. We will now consider spheres which have contact with an arbitrary given curve C given by its vector parametric representation in terms of arc length, where S is that such arc length of the curve capital C proper. Let P be a common point of C and a sphere S of radius R with center M, denoting by the vector A the position vector of that center M. We can represent S in the form the function g of x1, x2, x3 is equal to the quantity vector x minus vector A dot product with the quantity vector x minus vector A closed quantity. Then we have minus r squared, where r is the radius of what we're going to be calling the osculating sphere momentarily. This relation of these two dot products minus the square of the radius of the osculating sphere is equal to 0. In order that C, the curve, should have contact of first order with the surface S at the point P, we must have at that point P that the derivative of the function P ds is equal to dds of the function g x1 of s, x2 of s, x3 of s, which this derivative in terms of s of the function g is equal to the derivative of those dot products and such from the previous line, which is 2 times vector x minus vector A closed quantity times the first derivative of the vector x in terms of arc length, which is x dot in the notation of this book, which is equal to 2 times the quantity vector x minus vector A closed quantity dot product with the vector t, which is equal to 0. That is, the center M of any sphere which has contact of first order with the curve C at P lies in the normal plane N to C at P. And you can go back to the osculating circle stream, and you can see about that. You could also interpret it as like the osculating plane, of course, has your a point on the plane minus the point at the curve that your osculating plane is defined about. That's like z minus x. That's the first column. Then you have x dot in the second column and x double dot in the third column. You take the determinant of that equal to 0. That's the definition of the osculating plane. You basically follow those that determinant calculation in order to get what they just said. So it's not that bad. The radius corresponding to a certain choice of M, the center of your osculating sphere, can then be obtained from what we just calculated. The vector A is now of the form A equals the vector x plus the scalar alpha times the vector p plus the scalar beta times the vector b, where scalars alpha and beta are real numbers. We now assume that the curvature kappa of capital C curve at point P is not 0, and P is capital there to refer to the point, not the vector P, which is a part of the definition of the vector A that we're dealing with right now. In order that the curve C has a contact of second order with S, the surface, at the point capital P, then in addition to the things that we had just calculated, we must have at P that d squared P ds squared is equal to 2 times the quantity vector t dot vector t plus the quantity vector x minus vector A closed quantity dot product with t dot, referring to a derivative of this tangent vector t, is equal to 2 times the quantity 1 plus vector x minus vector A dot product with the scalar curvature times vector p, which is equal to 0. Might be a dollar short and a day late, but the vectors t, the vectors p, and vectors b here are not arbitrary if you're just jumping in from not watching any of the previous streams, which is encouraged and is totally okay. T is a tangent vector, p is the principal normal vector, and b is the binormal vector. These three are all tangent to the curve at a particular point, and they form what's called the moving trihedron, but T, P, and B are all orthogonal to each other, and it's a convenient way of assigning a coordinate system frame of reference when you're moving along points of these curves or surfaces. So that's all that T, P, and B are. By inserting what we just calculated as far as the vector A into what we just calculated for the second derivative in terms of arc length of this function P, then we find the condition 1 minus alpha times kappa is equal to 0. That is to say, alpha is equal to rho, where rho is the radius of curvature being referred to here at this tangent between the curve and the surface. This means that the two-parameter family of spheres with centers given by this vector A, which have contact at least of first order with C at P, we could have higher partial derivatives here if we want, possibly. With C at P, capital P, the point, not the unit principal normal vector, the point P contains a one-parameter family of spheres having contact of second order at least with C, the curve, at the point capital P. The position vectors of the centers of these spheres are of the form vector A is equal to the vector x plus rho, the radius of curvature, times the principal normal vector plus beta times the principal binormal vector, where kappa, the curvature, is greater than 0. Since beta may have any real value, then this representation of A, the vector, is a representation of a straight line parallel to the binormal and passing through the center of curvature corresponding to the point P. And this has gone over in the osculating circle section. This line is called the polar axis of the curve capital C proper at P, the point capital P. In order that C have contact of third order with a sphere S at P, in addition to the results that we had just gone over, we must have at P, the point, that the second derivative of P, not the point, but the function P, so d squared P ds squared, is equal to 2 times the quantity curvature times the vector T, tangent vector, dot product with P, the principal normal vector, plus the difference between the vector x and a, so x minus a, dot product with then this other quantity, first derivative of curvature, kappa, times the principal normal vector, P, plus not derived curvature, kappa, times the derivative of the principal normal vector, P dot. This is then equal to 2 times the quantity x minus a. And this x minus a is dot product itself with kappa dot times the principal normal vector minus the square of curvature times the tangent vector plus the product of curvature and torsion times the binormal vector, which then is all equal to 0. So we're going to continue the algebraic manipulation, insert a previous result for the vector A into what we just calculated for d squared P ds squared in order to obtain that the radius of curvature times the first derivative of curvature plus beta times curvature times torsion is equal to 0. And therefore, if torsion is non-zero, then at the point of contact, P, beta is equal to negative kappa dot times rho squared over tau, which is equal to rho dot over tau, which rho is the radius of curvature. So this is to say we're taking the derivative in terms of arc length of the expression for the radius of curvature, and we're dividing that by the expression for torsion in order to get beta. This means that the one parameter family of spheres with centers at given by this vector A that we had previously calculated, which have contact of second order with C, the curve, at the point P, in general, contains just one sphere, S sub 0, or S naught, capital S naught. This is referring to the sphere, not a particular value of arc length, which has contact of third order at least with the curve C at the point P. This sphere, capital S naught, is called the osculating sphere of the curve C at the point P. Inserting the value of beta that we had just calculated, we find the position vector A of the center of the osculating sphere, capital S naught, which is given by vector A equal to vector X plus rho, the radius of curvature, times the vector P, the unit principal normal, plus rho dot over tau, which is the derivative in terms of arc length of the radius of curvature divided by torsion, times the vector B, which is the unit binormal vector. And in this case, of course, we have, in order to not be trivial, that curvature is greater than 0 and torsion is non-zero. Torsion could be positive or it could be negative. If kappa dot equals 0 at P, the center of S naught, the center of the osculating circle, or sphere, the center of capital S naught lies in the osculating plane of the curve C at the point P and coincides with the center of curvature. From what we had just obtained for the center of the osculating sphere, we obtain the radius, capital R sub S, of capital S naught, which is capital R of S is equal to the magnitude of the difference between X and A, which is the magnitude of X minus A, which is equal to, in a Euclidean metric, the square root of the quantity rho squared plus rho dot over tau itself squared, closed quantity. If the curvature of a curve is constant, the radius of the osculating spheres is also constant. And the circular helix is of this type. Our beloved circular helix has an osculating sphere which is of constant radius. That's why it's our beloved circular helix example. Now we come to another theorem which is not going to be proven. Theorem 19.4. The center of any sphere which has contact of first order, at least with a curve C at a point P, lies in the normal plane to the curve C at the point P. The center of any sphere which has a contact of second order at least with C at a point P where kappa is greater than 0, that is to say, positive curvature, lies on the polar axis of the curve C corresponding to the point P. All these spheres intersect the osculating plane of C at P along the circle of curvature of C at P, which has a contact of second order, at least with C at P. The osculating sphere with center and radius determined by what we just calculated, respectively, has contact of third order, at least with C. And this video is getting pretty long, so I'm just going to close it off here, and I'm not going to do the problems. I might do that in the next video here, but osculating spheres were first considered by Nicholas Fuss in 1806. Nicholas Fuss is a Swiss-Russian mathematician, and he wrote about these in a Latin text, which is called De Spheris Osculantibus. De Spheris Osculantibus. So he wrote an entire text in Latin about Spheris Osculantibus, osculating spheres. But the formulas that we're using here are due to a gentleman by the name of Adhemar Jean-Claude Barrès de Saint-Venant. Adhemar Jean-Claude Barrès de Saint-Venant. And of course, if you look into this guy, de Saint-Venant, he taught math at, the French École des Ponts et Chaussées, the French school of roads and bridges, where possibly our famous engineers, Louis Leger-Vallée, Michel-Ange Lancret. They were both rock stars of the Pensées Chaussées. Yeah, and this guy, Adhémar Jean-Claude Barré de Saint-Venant, he was a teacher at L'École des Pensées Chaussées. And he wrote his book. I'm not sure, he may have written more. He probably did if he was, but he wrote Mémoire sur les lignes courbes non plans. And his theorem states that the simply connected cross-section with maximal torsional rigidity is a circle. So, merci beaucoup, Monsieur de Saint-Venant. I'm not going to read Mémoire sur les lignes courbes non plans ever in my life, but we have, some good ways to represent an osculating sphere, thanks to you. So that's it for today. Hope you guys have enjoyed the differential geometry stream. Leave a comment, like, subscribe, and I'll catch you in the next one. Peace.